All right, and looking at simple harmonic motion, we need to talk about pendulums. And so we're going to talk about simple pendulums and what exactly they mean. So a simple pendulum is just a mass suspended by a light string of length L. So it's just going to be this with some mass attached. So we got some mass M, some length of string L. That's what a simple pendulum is. Looking here, you can see the path a pendulum takes is an arc. So we can move it up an angle. So right here, the angle's actually going to be straight down, and then this angle will be an extension. The movement of a pendulum makes a sine curve. So a pendulum is simple harmonic motion. And then a free body diagram of a pendulum looks like this. And you can see how all of these work together. So gravity goes straight down. Gravity gets broken apart into x and y components, and tension of the string counteracts our y component. So what causes the movement, the net force that causes movement down, is always going to be mg sine of theta at any given point, and then the angle changes as it moves. So that's the math that's involved in the free body diagrams that you can use. The period of a pendulum, very similar to the period of a spring equation. Period of a pendulum is 2 pi times the square root of the length divided by the acceleration due to gravity wherever you're at. So outer space, Mars, Earth, sea level, top of a mountain. G will change the time period of a pendulum, and the length of the string will. But we'll talk about all the other variables and why they don't work also. So we got a yo-yo with a string that's 3/4 of a meter in length. What is the period of oscillation if the yo-yo is allowed to swing back and forth at the end of its string? So we want to find period. And we have all the information we need. 2 pi square root L over G. 2 pi square root, our length is 0.75. And G is, we're going to assume 9.8. And we get 1.7 seconds is our period. Very similar to the spring equation. So period mass. If we change the mass on the pendulum, as it goes up, since it has more mass, it has more inertia. If it has more inertia, it should move slower. But counteracting that's the fact that it has more gravity force, which means it should move faster. Therefore, they cancel out. Gravity and inertia cancel each other out. So changing mass of the bob, which is what that's called, does nothing to the period. Period and amplitude. Okay, so the farther we stretch it, so we start here. If we stretch it out farther, okay. So if we increase our angle, all right, we're changing the amplitude. In the second situation, the pendulum has farther to reach to go to equilibrium, but the restoring force, the gravity force, is larger. So even though we move it back farther, if the length stays constant, the restoring time will be the restoring force will be larger, so the time will be the same. So periods of equal length, pendulums of equal length have equal periods, regardless of where you start them at. Now, period and length. Now, this is why period and length work the way it does. So we'll take the same displacement angle, but we're just going to have a short and a long string. Okay? So the restoring forces are going to be equal. But look at the distance that needs to be covered here compared to the distance here, even if the angles are constant. This has a longer distance to go, therefore a longer string means longer period as opposed to shorter string, shorter period. If everything else is constant, mass and angle. Mass, of course, doesn't matter. So, big thing. Same restoring force, longer string, longer period. So, looking at the grandfather clock, you'll have weight at the bottom of a pendulum can be moved up or down by turning a small screw. So you got the grandfather clock, you got that weight down here, and it moves back and forth. But you can adjust that. You can adjust this length. And if your clock is running slower, we want to make it move, and it's not keeping time right, What do we have to do to the weight to make it go faster? Well, we want to decrease our distance travels because we want to have a shorter period. So we'll take our string and we'll make our string shorter. So if we want to shorten the string, okay, it will make it go faster, which in turn will shorten the period, and our clock hopefully will be back on time. So that's how you can adjust a grandfather clock. Move the string up or down. Up to make it speed up, lower it down, the bob down to make it slow down. All right, so we have a pendulum here, and this is a kind of a higher order question, but I like it. It has a string length of 0.627 meters, and it's attached to a mass of 0.25 kilograms. When we set it in motion, it completes one oscillation every 1.59 seconds. So we know our period. If the pendulum is held at rest in the vertical position and the string is cut, how long does it take for the mass to fall a distance of 1 meter? So the first question is, how do we solve this part? And you've done this part before in kinematics. Y equals y sub naught plus VOT plus 1/2 AT squared. All right. Our final position will be 1. Our initial position will be 0. Our initial velocity is 0. So it's going to be y is equal to 1/2. But our acceleration is going to be g t squared. Now, the question is, what is g in our location? That's where the rest of this information comes into play. Because we can use the period of a pendulum to find g. Okay? And so that's what we're going to do here. So we know our period is 1.59. And we know that our length is 0.627, and we're going to solve for g. It looks like it's a messy problem. First thing you want to do is square everything. So I go 1.59 squared. 2 pi squared is 4 pi squared. All right, times 0.627 over g. Put that over 1, cross multiply, and solve for g. I won't go all the way in detail into that, but I'll give you the answer. G in this location is 9.79 meters per second squared. I substitute that into there. My y is 1 meter. I can find my time. And my time, when I substitute in, should be 0.452 seconds. If you want me to do this math with you differently, come and see me and we can work through this problem together. That was another page, didn't need it. Okay, resonance is another term that'll come up. Resonance is based off something called a natural frequency. It's the frequency where an object isolates by itself. Due to wind or something like that, could get an object to start moving, that could be the force. And then rocking back and forth, bridges do this, but it will oscillate continuously. So resonance is a system driven at its natural frequency. And we'll talk more about resonance when we talk about sound. Just trying to give you a term here. One more thing to talk about is something called damping. Damping happens when an object starts. So let's say I start this thing going back and forth. If I just start it and then stop moving my hand, it will slow down and my amplitude will decrease to a point to where it'll stop. Damping is friction or gravity causing simple harmonic motion to slow. The only way to offset damping, add energy to the system. In this case, start moving it back and forth again, and then the amplitude will increase and we can get rid of the damping. But damping is just friction causing things to slow down.